Well, thanks very much for putting up with me for a third day. So yesterday we talked about how often the value of a polynomial is square. And today, as a complement, we're going to talk about how often is the value of a polynomial square-free. Well, maybe I should say what it means for a number to be square-free. So it just means that it has no non-trivial square factors. So number n is square-free. If for all primes p squared does not divide n. So no non-trivial square factors. Yeah. And so one question that you might immediately ask before you even think about polynomials is if you pick a random integer, what's the probability that it's square-free? So the question is, what is the probability that a random integer, whatever that means, I'll say what I mean in a second, that a random integer is square-free. If you pick an integer at random, what's the probability that you get something square-free? So how do you make this more precise? Well, more precisely, what is the value of, so say you take the limit as x goes to infinity of all natural numbers n less than x, such that n is square-free. Okay, so suppose you take the set of all integers up to x, all natural numbers up to x that are square-free, and divide this by the total number of natural numbers less than x. And then you let x go to infinity. So what's the value of that? So that's what we mean by probability of being square-free. Yeah. Okay, it's just the density of square-free numbers in the natural sense. And so probably many of you have seen before, the answer is this amazing occurrence of pi. 6 over pi squared is the answer. So I thought this was a really amazing thing when I first saw it. That doesn't mean factorial, by the way. It just means I'm excited. Okay. So the answer is 6 over pi squared, which is about 0.6, a little bit more than 0.6. So if you pick a number at random, the probability that it's square-free is more than half. It's more than 3/5, in fact. And so why is that true? That's good to know before one starts thinking about values of polynomials. So why is that true? Well, the heuristic proof is that, well, the probability that p squared divides a random number n, well, it should be 1 minus 1 over p squared, right? Because
not divide.
What's that?
Not divide n.
Oh, not divide n. So the probability that, so if you pick a random number, so fix p, you pick a random number n, what's the probability that p squared doesn't divide n? Well, the probability that p squared does divide n should be about 1 over p squared. So 1 minus 1 over p squared gives you the probability that p squared doesn't divide n. So that's just true. And the second point is that these conditions at various primes p should be independent. And that's rigorously true for any finite set of primes by the Chinese remainder theorem. Okay? But for infinitely many primes, of course you can't say that. That's the non-rigorous part of the heuristic argument. But primes p should be independent. It's true for any finite set of primes, not necessarily true for infinite set of primes. That has to be justified. But for finite set of primes, it's true. So, okay. So primes p should be independent, and so probability should be of being square-free should be just the product of being square-free at each prime multiplied over all primes p. So it should be product over all p of 1 minus 1 over p squared. And so how do you evaluate that? Well, product over all p of 1 minus, can everyone see down here? Is this too low? No, it's too low. Okay, let's start up here. So product over all p of 1 minus 1 over p squared, that should be the probability that you're square free, because each one is telling you the probability of being square free at that prime. Right? And then all the primes are independent. And to evaluate this, well, you can think of this as being 1 minus 1 over p squared inverse. And then this is the formula for an infinite series. Right? So we can write this as 1 plus 1 over p squared plus 1 over p to the 4th plus dot, 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 all inverse. And now when you multiply this over LP, you see that you get sum of 1 over n squared over all numbers n. Right? So this is just sum of 1 over n squared inverse. And sum of 1 over n squared is pi squared over 6, as you see in, well, I don't know, there are lots of ways to see that. Like in Fourier, if you expand the Fourier series of f of x equals x between 0 and 1, that's one way of doing that. So anyway, this is pi squared over 6, the value of zeta 2. And so this is 6 over pi squared. Okay, so that's the reason you get 6 over pi squared, the moral reason. Now how do you actually justify this step? Primes p should be independent. That's the key ingredient in making all of these kinds of proofs rigorous, and often the hard part. In this case, one can do it fairly easily. So maybe I'll show you that, because that's the kind of thing that one needs to generalize to do sieves in more difficult situations. So what's the rigorous proof? Well, so let's define this condition of being square free at a single prime. Let SP be a set of all n such that p squared doesn't divide n. So that's like being square free at p. And then let S be the set of all n that are square free. And since the n is square free, which means that you can think of S as just the intersection of SP over all primes p. Right? So now, if you suppose we only look at the numbers that are square free for all primes less than some bound, right? That we can do as an approximation of being square free. So if we take, say, the limit as x goes to infinity of, so instead of taking this, we'll just insist that n is square free for all primes less than some bound, say y. So let's say, so we'll take all n less than x such that n is in the intersection of SP for all p less than some bound, say p less than big M. And we'll divide that by n less than x, the set of all n less than x. I guess I should have put numbers here. Can't divide sets. Did I miss any numbers? Okay. Okay, so what is this going to be? Well, this is only finitely many. We're only imposing finitely many congruence conditions on the top. Okay. So the primes are actually independent. All these primes are actually independent by the Chinese remainder theorem. So this we can evaluate, right? So this will really be just the product over all p less than m of 1 minus 1 over p squared. Right? That's just true, because there's only finitely many congruence conditions that are being imposed on the integers, and that's the density of them. Okay. The probabilities are independent for finitely many primes. And then if you now let, right, so this set contains the square free numbers, right? So only as you impose more and more, as you increase m, right, this top is only getting smaller, right? And this is also getting smaller, as it should, right? And so if you let m go to infinity, what is that saying? Well, that's saying that this thing, right? Well, at least the lim sup. So I guess maybe I'll write it out. So the lim sup. So therefore, that implies that if you take the lim sup, so n less than x, n square free, right? So that's certainly going to be less than or equal, right? Because this is just getting smaller and smaller. That's always going to be an upper bound for the density of square free numbers, right? So if you keep imposing more and more things, this constant gets smaller and smaller, and it approaches something, namely 6 over pi squared. That's clearly, that's at least, right, we can say that's the lim sup of the density of square free numbers. Right? So that we can certainly say is less than or equal to product over all p of 1 minus 1 over p squared. So that's what it says, just taking the trivial thing and letting m go to infinity, saying that certainly couldn't be bigger than this, the density, because for any finite number of things, you get arbitrarily close to this. If you put arbitrarily many finite conditions of being square free, right, at bounded primes, you can be at most arbitrarily close to this, and so this is the biggest that the density of square free things could be, right? So an upper bound is very easy. If you just think about it, you just impose more and more conditions, and that gives you this as the upper bound, which is 6 over pi squared as an upper bound. So the lower bound is what's difficult in these problems. To get a lower bound, well, you note that if you take the intersection, which we just computed, right, the density of, so if you take all p less than m, the intersection of sp, that's the density we just computed to be this. This is contained, well, it's certainly contained in the set of all square free numbers, union the stuff that we missed over here, right? So this is these are the numbers that are square free everywhere for primes p less than m. But it's missing the things so this is missing numbers, so union p bigger than or equal to m of sort of the multiples of p squared, right? So if you take all the square free numbers and add to that set all numbers that possibly are multiple of p squared for p bigger than m, then you'll get all the numbers that are square free at p less than m, and possibly having square factors at bigger than m, right? So this quality is clear? Yeah. And so what that means, that if we're trying to compute the density of this, that's at most the density of this, which we already computed, minus the density of that. Right? And so if we write like a lim inf, since we already got a lim sup, we try to do a lim inf, so x goes to infinity of the number of n less than x, n square free, okay, over number n less than x. Well, that's going to be greater than or equal to this density, which we already know. It's just that. So product p less than m, 1 minus 1 over p squared, minus the sum of the densities of each of these guys. Okay, well, what's the sum of the densities of each of those guys? Maybe I'll put it over here. Well, you have to sum over all p greater than or equal to m. The number, and what does this mean? This is multiples of p squared. So we want to know the number of multiple of p squared less than x, right? So we're sort of summing. So number of p squared less than x, that means right away, actually, that we only have to consider p that are less than x, although it doesn't matter. But right, if we're only looking at multiples of p squared that are less than x, then we can actually make p less than root x, right? These are the multiple of p squared, and we're only counting up numbers up to x. So p squared is less than x, p is less than root x. So we only have to look at, which is significant, though in this particular case it doesn't matter so much. How many numbers are there that are multiples of p squared less than x? Well, it's something like x over p squared. Exactly, it's this, right? That's how many numbers that are multiples of p squared up to x. That's why it doesn't matter. If we put this, you automatically get 0 in this formula, right? So this thing divided by x, right? If we have, right, so this is as x goes to infinity of this thing. But the point is that this thing is less than or equal to sum, all right, 1 over p squared for p bigger than m. And the significant thing here is that 1 over p squared converges. So if you let m go to infinity, this thing approaches 6 over pi squared, and this thing approaches 0, because we're summing a convergence series starting at a higher and higher point. So let m go to infinity shows that lim_inf as the right of the thing we wanted is less than or equal to, greater than or equal to 6 over pi squared. And that combined with the fact that the lim sup is less than or equal to 6 over pi squared, that shows that you actually have equal to pi squared. So the density of square free things is actually equal to pi squared. So what was the key thing that allowed us to get the lower bound? It was the fact that between 0 and x, we could exactly count the number of elements that are multiples of p squared and get an exact formula, or at least a very good bound. And that's because the congruence condition, mod p squared, that tells you whether something is a multiple of p squared, it's a very easy one. You just have to be 0 mod p squared. Okay, and that you can imagine that could be more complicated if you were looking at a more complicated expression and asking when is it a multiple of p squared. Okay, but here it's easy, and that's what allows you to prove 6 over pi squared. Okay, so that's sort of the fundamental argument that I'll use throughout the talk. So any questions about? So this is a simple proof of why the density of square free numbers is 6 over pi squared. And if you're more careful through the argument, you can actually show that the number of square free numbers up to x is 6 over pi squared times x plus an error term, which is on the order of square root of x. And if you're careful with this argument, then you can actually get the error term. But I was just interested in the main term, and this is probably the simplest thing you can do to get the main term. Is that clear? Okay, so now on to the more general question, which is suppose you take a polynomial. So let f of x1 through xm. So it's going to be a polynomial in m variables. Be an integer polynomial. Then we can ask the more general question. What is the probability that a value of f, so value of f, I just mean value of f taken at integer arguments, right, for x1 through xm. What is the probability that a value of f is square free? So I didn't talk about this yesterday, but a lot of the results that I mentioned yesterday involved doing square free sieves to a number of multivariable polynomials. And we needed to know that those multivariable polynomials took square free values in order to compute some of those rank bounds. Which is the reason I got into this question in the first place. So it's probably that a value of f is square free. So let's make this more precise too, just so we know what we're talking about. So more precisely, so what we're going to do here is we're going to I was calling it x before, so maybe I'll call it n. So we're going to take a box centered at the origin, getting bigger and bigger, and we're going to look at the values of f on the lattice points in that box. We're going to count how many of them, the proportion that are square free of those values, and take the limit as that box size goes to infinity. And that's what it'll mean to talk about the probability that a value of f is square free. So in other words, we're going to take the number of x in the interval minus n to n. Okay, so this is a box of size n in m-dimensional space, right? And we're interested in the lattice points. So intersect with z to the m. Such that f of x, right? So x you're thinking of as a vector with m components. This is f of x is square free. And we're going to divide by the total number of points in that box, this box here, which is, I guess, 2n plus 1 to the m. Okay. So the question is, what is that value if it exists at all? It's not clear it exists. It wasn't clear when we asked the easier question either, but we showed that it does exist. Yeah, so what's the probability that the total number of things that are total number of values that are square free in a box divided by the size of the box, and you let the size of the box go to infinity. That's the probability that we're defining, and we're asking whether it exists. And that's the probability of being square free. And the conjectured answer. So there's a general conjectured answer for this. So I'll just call V conjecture from now on, because that's what I want to talk about today. So the conjectured answer is that, well, it exists, and it should be product over all p. All the primes p should be independent, just like they were in the case we were counting general square free integers. And it should be 1 minus, well, something over p squared, but well, let's see. I'll say 1 minus cp over p to the 2m. So the reason it's p to the 2m is that there's going to be a congruence condition mod p squared, right, on m-dimensional, right, on m-dimensional lattice points. So the number of m-dimensional lattice points mod p squared is p to the 2m, right? Right, z mod p squared to the m. So the answer should look something like this, where cp is what? It's the number of solutions to f of x is congruent to 0 mod p squared in z mod p squared to the m. Right? So cp is equal to the number of x in z mod p squared raised to the m, right, such that f of x is 0. Right, mod p squared. I'll say it again just to be clear. So everyone see this generalizes what we right, so this in particular for the polynomial, right, so for just f of x being the simple polynomial x, right, this recovers the 6 over pi squared result. Yeah. Product over p of 1 minus, what is cp? Well, it's the number of solutions to x congruent to 0 in z mod p squared z. There's only one thing that's 0 in z mod p squared, which is 0. Okay, so there's 1. So you get 1 over p squared. Right. So that's what gives the 6 over pi squared. Okay, so this is the general conjectured answer, which gives the usual answer for the number of square free integers. But this is what should be happening for general polynomials. Yeah, it's a totally natural conjecture. Okay, so the question is, why can't you just prove it the same way? Here's the proof. Okay, so we've already proven it for f of x equals x. For quadratic polynomials, right, in one variable, so say f of x, essentially the same proof does work. Yeah, essentially same proof. Right, as in the case f of x equals x. The reason being that this 1 over p squared converges very fast. Even if it's just 1 over p to the slightly bigger than 1, right? If this exponent 2 was even just slightly bigger than 1, that would be good enough. So the point is that here we were counting up to x. So p could go as big as root x, and that was fairly small. But when your polynomial has bigger degree, right, if you plug in a number between 0 and x into a polynomial of bigger degree, say degree 3, then your value could be as big as x cubed, which means if p squared divides the value of the polynomial there, it could be as big as x to the 3/2, right? But you're only counting, your variable is only going in a range of 0 to x, and your prime could be as big as x to the 3/2. Well, that's the problem. So suppose the congruence conditions mod p squared are really complicated, and you want to know how those solutions to 0 mod p squared lie in the interval 0 to x. So somehow you're counting solutions in this range 0 to x, and yet your congruence conditions are modulo a p squared, which is way bigger. And so it could be that your congruence conditions, your CP that you're counting, maybe all the elements of your CP are lying like over here, right? So your solutions to 0 mod p squared all your p's could be conspiring to put all those solutions beyond the region that you're counting in. Or it could do the opposite. It could just put them all in this little tiny place where you're counting. So even though CP over p to the 2m is small, it may be coming out huge because all the solutions are conspiring to be in that little tiny interval that you're counting in. So the problem is that p squared can start to get much bigger. The p's that you care about, those p squareds could start out to become way bigger than the interval in which you're counting in. And so for higher degree polynomials, to prove the formula, to prove the conjecture. So I'm still talking about one variable, in one variable. To prove the conjecture, one needs to know, well, that these CPs, these solutions that we're counting, are somehow not all conspiring to be on one side or the other, that they're sort of equidistributed. So that the proportion that you're expecting in this whole thing, which is something you can compute, is about the proportion that you get in there. So that's a kind of equidistribution result. That the number of solutions that you expect here is actually what you get. That's the equidistribution. So one needs to know some type of equidistribution. Of the set, which is, well, this one, right? Of this set in the interval 0 to p squared minus 1. And something weaker than that, of course, is okay, right? As long as you know that it's equidistributed, as long as the number you expect here is coming out to be right, then that's good enough. But if you know basically that your solutions are essentially equidistributed in here, then if you just count in this interval, you'll get the right number of, right? What you're approximating your fraction of things to be is actually well represented, even in your shorter interval. Okay, does that kind of make sense? Yeah. Okay. Okay, so that's what makes the problem hard, especially as the degree gets very big. Then your primes that you're considering start to become way bigger than the interval in which you're counting the congruence condition. So unless you know some kind of really good equidistribution, it's hard to prove that this is exactly the formula you have even when p gets big relative to x. Okay. So I should mention, so for cubic polynomials, you just need a little bit more of equidistribution, and that's actually now that's known due to work of Hooley. So for cubic polynomials, that's an equidistribution result. Exists due to Hooley. And so for linear and quadratic and cubic polynomials, one does know this conjecture in one variable. So conjecture true for one variable polynomials of degree less than or equal to 3. And that's really where it stops, very abruptly, in the sense that there's not a single irreducible degree 4 polynomial in one variable known for which the conjecture is true. I mean, it's provably true.
Unless CP is 1 and CP is 0.
Oh yeah, that's true. Yeah, if you arrange for CP to be 0, Or 1, yeah, 1. Yeah, they can probably prove it, yeah. But I think for an irreducible polynomial, it's hard to arrange, yeah. So for example, yeah, so I think it's true that no irreducible quartic is known. For which conjecture is true, at least non-trivially true. So here's one of my favorite questions. So if you take the simplest polynomials, let's take x to the 4 plus 1. Let's not even talk about the density in the conjecture. Does this take infinitely many square-free values? Infinitely many, that's all I'm asking. Even that's not known. So x to the 4 plus 1, does it take infinitely many? I'm not even asking for it to be a positive density or this density. Just want there to be infinitely many, even if it's 0 density. Does it take infinitely many square-free values? That's an open problem. So even that's unknown. Unless, maybe it is known. So let me say something about that. Terry just got what I was saying. Yeah. Maybe I'll say one more thing, which is, so if you add variables, it doesn't really help the situation very much. It's still all equally unknown. If you have multivariable polynomial in which the polynomial with respect to the one, if you just look at it as a polynomial with respect to one of the variables, has small degree, then you could just use that last variable in which the degree is small to try to apply these results. So that's the case where you can handle multivariable polynomials. So for multivariable polynomials, if degree is small with respect to one variable, then you can reduce to a one variable case. At least sometimes, so it depends on. And sometimes reduced to one variable case. The other place where one can handle multivariable polynomials, if the number of variables, so if number of variables is way bigger than the degree, then can usually handle. So not always, I'll say something in a second, but basically you can always handle using the circle method to prove the conjecture. So that's assuming that the polynomial is not a composition of some smaller degree polynomials or something. But if it's a polynomial in which the circle method applies, where you have lots of variables compared to the degree, then the circle method allows you to prove the conjecture. So there's this intermediate range where the number of variables is about the same order as the degree, and there none of the known techniques apply. Okay, so that's essentially what's known, almost essentially what's known. But I should say that there's an amazing argument of Granville. And because of this, one has to be careful about saying what's unknown. So that Granville has shown that the ABC conjecture so what's the ABC conjecture? The ABC conjecture says basically that if you have two numbers that add to a third, then if you take, then C has to be at most a constant times all the primes dividing A, B, and C, just counted once. 1 plus epsilon. So that's the ABC conjecture. So it's saying that you can't have lots of prime divisors of all three of those things simultaneously if they add to each other. So this conjecture, famous conjecture in number theory, implies the conjecture.
What is it, less than what? Epsilon?
Oh yeah. This depends. This constant just depends on epsilon. Yeah. So in other words, it's less than a constant times this, where the constant depends on epsilon. Yeah. So this implies the square-free conjecture. So the square-free conjecture. So that's kind of remarkable, and so that's why I'm saying that maybe this thing is not necessarily unknown, because there is a proof on the internet of the ABC conjecture, which you can read or try to read. Yeah. So this is one of the really amazing consequences. I mean, if you look at if this work of Machizuki is true, then this is one of the amazing problems that it would imply immediately, among many others. So all square-free sieves will suddenly be very easy if the ABC conjecture is true. And I should note that Poonen has generalized Granville's result. So still assuming ABC conjecture, generalized Granville to multivariable polynomials.
Does Granville need the ABC conjecture over every number field, or just over the?
It depends on which form. Let's see. He does. Yeah, in the paper he does state it over every number field for some reason. I'm trying to remember if it's used.
I mean, I think for this particular problem, you don't need it.
Yeah, but in general, you have to go over the splitting fields. Yeah. The Poonen has generalized Granville to multivariable polynomials. So this was for one variable, but in fact, the ABC conjecture almost implies this conjecture for multivariable polynomials. Poonen actually proves something slightly weaker in the multivariable case, which I won't get into. Technically, it's slightly weaker, but basically, that theorem is proven. Okay, so that's sort of what's known without ABC up to there, and then with ABC, you basically know everything. Not except this, for multivariable case, it's slightly weaker, but I suspect that could be fixed. So ABC basically implies the square-free sieve for general polynomials. Okay, but without ABC, basically we know for one variable polynomials of degree less than or equal to 3. We know multivariable polynomials where it's small degree and at least one variable, or we know the case where the number of variables is much larger than the degree, in which case you can use circle method. So what I wanted to talk about in this lecture is some new cases of the square-free conjecture. That can be proven without ABC. So without ABC. Of course, I'm sort of rooting for ABC to be true, but for now, when I need certain results, I still can't say by ABC. But maybe soon. Okay. But in any case, the techniques that I want to talk about are useful for many other sieves, not just the square-free sieve, but this is sort of an example of a kind of problem, a square-free sieve, that can be done with a new algebraic geometry, algebra geometric technique. So these new cases have the property that the number of variables are about the same size as the degree. So it's a case that and the degree is large. So the degree is greater than 3 in each variable. So it's not a case that could be reduced to the one variable case, and it's not a case that could be done that could be reduced to a circle method type of argument. Okay, so what are these new cases? So some new cases, the square-free conjecture without ABC, where the number of variables is about the degree, and the degree is large in each variable. So these polynomials, for which we can now prove the correct density of square-free values, are certain, well, they're certain invariant polynomials for the action for a representation. So for the action of an algebraic group on a vector space. Maybe I'll give you one example to keep in mind as I describe the method. Now, if you remember in yesterday's talk, some of the results about rational points were proven by mapping rational points into lattice points in a representation of an algebraic group on a vector space. And a lot of times, in order to get good bounds, one needed to know that the invariant polynomials were taking square-free values. That reduction was very important to the counting argument, not to the map, which I described explicitly, but then to count those points and to do a sieve to just capture the image of that map from rational points to lattice points. One needed to know that the invariant polynomial was taking the correct density of square-free values. So it was exactly this situation, which is why we worked very hard on these particular polynomials, given that the general methods do not apply. But then suddenly, this method started applying to things that didn't naturally come up there, but are interesting for other reasons, and I'll explain that in a second. So one example to keep in mind, because it's a polynomial that one can explicitly write down, if you look at the discriminant. The discriminant polynomial of a polynomial. Okay, so the discriminant is a polynomial, right? Like b squared minus 4ac is a polynomial if you're talking about discriminant of a... So discriminant polynomial of a polynomial. Let's just say a cubic polynomial so I can be explicit. Discriminant polynomial, but the technique works for any degree polynomial. Let's talk about discriminant polynomial of a cubic polynomial. Or let's say binary cubic form, just so you can see the group action. But really, I'm just talking about a discriminant polynomial of a cubic polynomial. So everyone learns the discriminant polynomial of a quadratic polynomial is b squared minus 4ac. But for some reason in school, we never learned the formula for the discriminant polynomial of a cubic. So if the cubic form is ax cubed plus bx squared y plus cxy squared plus dy cubed, then the discriminant, so let's say this is f of xy. So it's just a cubic polynomial. Then the discriminant of f, instead of b squared minus 4ac, it's the degree 4 function in a, b, c, and d, which because I play around with so much, I remember. It's not so bad, right? Okay, so the technique I'm going to describe now applies, for example, to this polynomial. Now, that's not terribly impressive because if you look at this as a function of d, it's quadratic. So one could presumably do it by isolating, right, treating this as a polynomial d squared and reducing to the way we do one variable for a quadratic. But the technique I'm going to apply applies more generally to this. This is just for illustration, so you can explicitly see it. But then it applies to many polynomials where all the degrees are huge. But still. So the point of this polynomial is that this polynomial, disc f, is invariant under the action of SL2. So SL2 naturally acts on binary cubic forms by linear change of variable, right? X can be replaced by a linear combination of x and y. Y can be replaced by a linear combination of x and y, and you get back a binary cubic form. And in that action of SL2z, the value of the discriminant doesn't change. Just like in the case of binary quadratic forms, you have ax squared plus bxy plus cy squared. If you act by SL2, the value of b squared minus 4ac doesn't change. So disc f is invariant, and that's why I wrote it as a binary cubic form, so you can see the SL2 action. If you just write it as a general cubic polynomial, then you don't see it. Right? If you just write it as x cubed, x squared, x1, then you wouldn't see it. But if you write it as xy, then you see this action of SL2. And that you can take advantage of SSL2 to find square-free values. OK, so how do you do that? OK, so the main idea is to somehow use this action of SL2. But first main idea is actually independent of any group action, which I've already, just this way of thinking about it actually turns out to be useful for many of these kinds of square-free problems. Main idea is that a polynomial so a polynomial value, let's say, can be a multiple of p squared in two very distinct ways. And it's important, I realize now, is that it can be helpful, even important to keep track of them separately. So the first way, say, call it A. So it can happen for mod p reasons, or it could happen for mod p squared reasons. OK, so what I mean by that? Well, maybe I'll just give you an example to illustrate. So, so what does it mean to be for mod p squared reasons? Well, suppose your polynomial f of xy, just to give you a really simple example. Suppose just xy. Okay. So xy sometimes takes multiples of p squared as its values. And there are two ways that could happen. One is that both these guys are multiples of p. And that then it's becoming a multiple of p squared for mod p reasons, I say. Why? Because if you changed x and y to something else mod p, each of them, it'd still be a multiple of p squared. So the reason it was a multiple of p squared was really for mod p reasons. So the case where x and y are both 0 mod p, that makes this a multiple of p squared. And it does it for mod p reasons, because if you change the variables mod p, it'd still be a multiple of p squared. Okay. And then for mod p squared reasons would happen, for example, if x was not congruent to 0 mod p, while y was congruent to 0 mod p squared. This is really so now if you plug in xy into f of xy, right, you are getting a multiple of p squared, but it's not for mod p reasons, because if you switched x and y mod p, it wouldn't always be a multiple of p squared. Only if you change them mod p squared would they continue to be a multiple of p squared. So these are two distinct ways that you can be a multiple of p squared. Right? So in this case, it's very easy to see, but in general, that has to be worked out. When we're computing that CP, some of those CPs are coming from mod p reasons, right? When they were counting that set counted by CP, some are happening for mod p reasons, and some are happening for mod p squared reasons. And that can vary for different polynomials. OK, so to handle A, one can actually use an argument from algebraic geometry. So to handle A, we have the following general theorem that handles A in general. Square values for mod p reasons, and actually does a lot of other kinds of sieves that have been useful. So let me show you. It's a sieve that's basically, so this is the following version of a theorem of Ekadal, who was an algebraic geometer who just passed away last year. Great algebraic geometer. So a version of a theorem of Ekadal. And so I like to call this the Ekadal sieve. So here's the theorem. So suppose y, but y, maybe, let's see, should I state it in general? I could probably say it. OK. So OK, let y be any variety in m-dimensional space. Of codimension k. So that's just codimension k just means it's basically defined by k equations. Okay, so it's a zero set of k simultaneous equations. And we want to make sure it's defined over z. So the equations are given by integer polynomials inside with m variables. Okay, so y is basically defined as a 0 set of k integer polynomials. Okay, so if you do algebraic geometry, we're asking for a closed subscheme of codimension k inside affine M space, defined over Z. Okay. Okay, so then here's the theorem, is that if you count the number of elements in minus n, right? So in a big box, well, lattice points, such that A mod p, if you look at A mod p, says that A mod p lands on the variety over fp, on the reduction of y mod p. So if A mod p is contained in y of fp, okay, for some p bigger than m, so m is going to be some big number. So this is kind of a tail estimate that we had just right when we're computing densities of square free values. Remember, we had a sum from p bigger than m. We wanted to know bad stuff wasn't happening too much when p is bigger than m. This is going to be what we'll use to handle such tail estimates in general. So A mod p lands on the variety for some p bigger than m. Okay? So we want to count the total number of things in the box, such that if you reduce mod p, you land on this codimension k variety for some p bigger than m. Well, so we have a good estimate for this. This is O of n to the m over big M to the k minus 1 plus n to the m minus 1. Okay, so the total number of things in here is n to the m. And we're saying we're getting a saving. If m is big and k is at least 2, right, then this is, right, if the variety is at least codimension 2, this is a saving. This is always a saving. So this is a good estimate. If the codimension is at least 2, and m is big. So maybe, let's say a proof very quickly. So I don't want to tell you the idea of the proof of this because it's really neat. Let's just stick for, let's say, proof for k equals 2. So when you have a codimension 2 variety, it turns out, without loss of generality, you can say y is defined by, say, 2 equations, f of x1 through xm minus 1, and g of x1 through xm. So the point is that y, if it's codimension 2, is going to be defined by 2 equations. And you can always do some algebra to remove at least one variable from one of them. Right? Just clear out one variable from one of them. And you can say that y is defined like this, where f and g are integer polynomials. So now what you can do is you can fix x1 through xm minus 1, fix those values of which they're n to the m minus 1. And for each of those, you plug it into f, and you get some number, which you want to be, well, you want it to be 0 mod p. Right? You want it to be, y is defined as being, these polynomials being 0 mod p. Right? Y of fp means the point such that both of these are 0 mod p. If you plug in x1 through xm minus 1, you get some number here. It only has a bounded number of factors p bigger than m. Right? So unless it's 0, you have to take care of that separately. Right? If this turns out to be 0, well, then you have to treat. That doesn't happen very often either. Otherwise, it's some number. It only has a bounded number of prime factors p bigger than m. So yeah, right. So m will usually be some small power of n when you'd use this. Yeah, maybe it's good to say bigger than n to the epsilon or something. Yeah. So then if you plug in, you fix these x1 through xn minus 1, you plug it into the first polynomial. That has only a few prime factors p. And then that g then has to be a multiple of p. And you have one free variable to make it a multiple of p. It's a polynomial in one variable. that only has finitely many roots mod p, bounded number of roots mod p. Okay, so an fx1 has only bounded number of prime factors, p bigger than m, and for each that's p, g of all those fixed values xm equals 0 mod p, right? Mod p has a bounded number of solutions. Namely, the roots as a polynomial mod p, right? And whatever the degree is the bound of g as a polynomial in xm. It's only bounded number of roots. Roots, solutions? I don't know what you're supposed to say. Solutions. Mod p. So total number of xm right, total number of xm is big O of 1 plus, and then you have some finite number of conditions mod p, and your range of xm is like n, right? So n over p is the most you could really get there. 1 plus n over p. Right? And p is bounded by m, so basically you could say n over m is the worst you could really do there. And so if you take this thing and you multiply by n to the m minus 1, then you get exactly that. There's the n to the m minus 1, and there's the n over m, k is 2. Right? So total number of xm is this, for given fixed values of this, of which this had n to the m minus 1 possibilities. So that's what gives that. And you can generalize this to general k to get sieve estimates if you have things of higher codimension. Okay, so how to use this? So to handle A, okay, so that's the end of that proof. I skipped lots of details, of course, but that's the idea, right? You use two polynomial equations, bound the number of prime factors here, and then for each of those primes you can bound here. So this allows you to handle many p's at once, instead of handling each p separately like we did in the proof of the density of square-free values. That's the advantage here. It handles all p bigger than m simultaneously. Handles the total sum of the tail estimate instead of the individual terms. Okay, so to handle A, in other words, for mod p reasons, values of things becoming multiples of p squared, what you do is you just use so the point is, if f is a multiple of p squared, if f of x1 through xm is a multiple of p squared for mod p reasons, then its derivative with respect to the, say, xm is also going, right, they're both going to become 0 mod p. So both of these will be 0 mod p. So if f of x1 through xm is a multiple of p squared for mod p reasons, so then this will be 0 mod p, since it's 0 mod p squared, but even its derivative with respect to the last variable will also be 0 mod p. Right? Because if it's happening for mod p reasons, that means that as a polynomial xm, it had like a multiple root. And that's what was causing it to be a multiple of p squared. So we use this fact, the fact that this happens when it's congruent to 0 mod p squared for mod p reasons. Okay, so this can always be done, and I'm not using anything but any algebraic group or anything for that. So the real problem in the sieve, given this theorem now, is to handle cases of B, right, where it's really, you're becoming a multiple of p squared really for mod p squared reasons. To handle B, okay, well, here's the trick, is that you use the action of the group. So say the algebraic group was G, use some rational transformation on the variables, use the action of G of Q to transform B to A. Okay, so for example, in this silly situation, suppose you were, what's the group that's acting on this polynomial for which it's the invariant polynomial? well, GM, right, the multiplicative group naturally acts on it. If you scale x by lambda, you can divide y by lambda. That's an action of a group. And if y was a multiple of p squared and x was a multiple of p, x was not a multiple of p, well, you could scale this by p and scale this by p. And suddenly you've moved case b to case a. So a lot of times you can, and for lots of polynomials, I mean, this was a really trivial example, but for example, this polynomial too, you can actually always do that. So to handle, use the action of g of q to transform b to a, and then use the theorem. Okay, now there's something slightly wrong with that, which is that when you do, like why would that not immediately work here? Well, it's because the sizes of things have changed. Right? So when you do a transformation in g of q, you may have changed the size of the variables. You may have left the box. So use the action of g of q to transform b to a, and then use the action of g of z. So you also need the fact that g of z is big, which it's not here, although you can still make this work in this case too. But it's not, this case is not terribly interesting anyway. It's just for illustration. Then use g of z to restore sizes of the variables. Because if you went way out of the box, then it wouldn't be useful. So if g of q is big enough so that you can always transform b to a, and if g of z is big enough so that you can always restore sizes of variables, then that's perfect. And that's a case when you can always get the density of square free values. So let me just end by telling you how to do it for the discriminant of f. So e.g., discriminant of f is a multiple of p squared for mod p squared reasons, implies that there's an SL2 transformation such that f of xy, well, I'll use the same letters there. It implies that after SL2z transformation, p divides c and p squared divides d. So this is exactly the situation. So you analyze the polynomial and you work out when it's a multiple of p squared for mod p squared reasons. It turns out for this polynomial, it happens exactly when p divides c and p squared divides d. So for example, then every term will become, you can see, will be a multiple of p squared. If p divides c, that's a multiple of p squared. If p squared divides d, that's a multiple of p squared. P divides c, multiple of p squared. P squared divides d, so that's a multiple of p squared. Yeah, multiple of p squared. And it's really happening for mod p squared reasons there, so we have to handle that. Okay, well, what you do is you do a transformation where you divide this out by p squared, you divide this out by p squared, this by p, this you keep the same, this you multiply by p. And suddenly the mod p squared conditions disappear. So if you do the transformation a, b, c, d, pa, b, pc, oh sorry, c over p, d over p squared. Well, this kills the b-ness. Yeah, this kills the b-ness. That's good enough. You know what I mean by that? Okay, so suddenly the solution that you had to make it a multiple of p squared for mod p squared reasons, that new solution is now actually not even a multiple of p squared. Sometimes you do transformations where it still remains a multiple of p squared, but it's for mod p reasons. So whatever's happening here is suddenly for mod p reasons, and then you can apply a. And so that handles the square freeness of this. It also handles the square freeness of discriminants of elliptic curves and of coverings of elliptic curves, which is what we were using yesterday. It also handles, like if you take ternary cubic forms, the discriminant of that, ternary cubic form is a genus 1 curve. If you look at its discriminant, we can now prove by using these methods that takes the correct density of square free values. So discriminants of just plain cubics take the correct density of square free values. And just to tell you that the circle method wouldn't work on these things, and that you couldn't always reduce it to a small variable case where it's just degree 2. One case that works is there's a unique invariant polynomial, discriminant polynomial on the representation wedge 2, 5, tensor 4. And here, there's a unique invariant polynomial which has degree 40, and it's 40 variables, right? Because it's 10-dimensional. Degree 40 and 40 variables. So when I was saying that the degree had to be similar to the number of variables to be away from situations where that can't be handled anymore. Here they're literally the same. Degree 40, 40 variables. And these techniques work on this particular polynomial. And for this space, this was used to show that the density of quintic fields, the number of quintic fields of bounded discriminant is what you expect it to be, even if you impose arbitrarily local conditions. And for that, you need to know that square-free discriminants occur with the right density, and these techniques work to do that. So that's an example. One last observation. So what's been happening lately is that sometimes we have polynomials that don't have symmetries that do what we need it to do. And amazingly, you don't always need that. What you can do instead, well, suppose the group of symmetries is too small. Then a lot of times what you can do is you can embed your vector space into a bigger vector space that has more symmetries. And when there are more symmetries, then there's more room to transform B's to A's. And you can often, so even if your polynomial that you started with didn't have enough symmetries, if you embed it into another space where the invariant maps to the invariant of the bigger space, and there we have more transformations to transform B to A, then you can actually handle lots of polynomials that didn't satisfy this property because you could map it into somewhere that did. And so that's allowed one to handle general polynomial discriminants and many other polynomials that don't have very many symmetries.
These are linear maps when you embed, or?
Not always, actually. Yeah. So you don't even need that. So what is the generality of this method? I don't know. It's seeming to handle a lot of things, but I don't know what the generality is. It's sort of in this. That's what a lot of us are working on right now, trying to see what can actually be handled with this and what can't. So I don't know the answer. So I think I'll stop there. Thank you so much for